I'm Lukas Biewald. I'm the founder and CEO of a company called Weights and Biases, and we make tools for machine learning practitioners. And prior to that, I was the founder and CEO of a company called Figure Eight that made labeling tools for machine learning practitioners. So I've been working with machine learning and deep learning for quite a long time, and hyperparameter tuning is something that's near to my heart because I think everyone should be doing it, and there's lots of best practices. And so today I'm going to talk about hyperparameter tuning and visualization in deep learning specifically. And I know there's a wide audience here. So for non-practitioners, my hope is that your takeaway is really what hyperparameter tuning is and why it's important. And for most of you, I'm thinking, who are ML practitioners, I'd really like to go into the various patterns that I've seen that makes hyperparameter tuning work and not work, and also specifically explain a partnership that I'm really excited about with Ray Tune specifically, and my company Weights and Biases, that makes it easy to do good hyperparameter tuning patterns and hopefully makes your models perform better. So let me get into it. All right. So I want to make sure that I define what hyperparameters are. This is probably familiar to most of you. The most common hyperparameters that you would think of are things like learning rate, which controls how fast your model learns as it sees new data, or something like model architecture, which wouldn't typically be a number. It would be, a string that would mean the type of model we're working with. So it could be ResNet or Inception with vision-based models. But really, I want to take a expansive definition of hyperparameters. So it's kind of any input to your model that'll make it behave differently on its training data. To give you a concrete example of hyperparameter tuning, I'm going to take a very, very simple model. So here our x-axis is the input and the y-axis is the output. So we have a one-dimensional input and we have a single-dimensional output, and we want to fit a model to these blue points that you see on the top. So the simplest model we might think of is a polynomial regression. And a polynomial regression really, it has one hyperparameter that you might think of, which is the degree of the polynomial. So if we set that degree to 1, you get the model on the left, you get the single line that doesn't fit the points very well, but seems like a safe choice. If you set that hyperparameter to 3, you get more of a curve that probably gets closer to the dots and seems like maybe it fits that data a little bit better. And then if we set that hyperparameter, that degree to 8, we have an 8-degree polynomial and it perfectly fits our points, but really doesn't capture the essence of the data very well. And already you might be thinking, how do we decide what the best hyperparameter is? We can, sweep through them and try lots of different values, but we're going to have a good evaluation function that tells us which is the best, and which is the best really might depend on the situation that we're in, what we're trying to do with our model. I also want to mention something that's not traditionally included in hyperparameters, but is becoming increasingly important, which is data pipeline hyperparameters, or attributes that affect things upstream of your model. And I really want to include these. Whenever I say hyperparameters in this talk, I really mean these because these can be the most important parameters that affect the quality of the model that you build. And with data augmentation, we introduce a lot of these, right? So typically, if you're making a vision model these days, you wouldn't just feed in, say, this picture of the cat on the left. You would modify it a little bit to make to add noise to your model and also make it seem like you have more training data than you actually do. So a simple thing to do might be rotate. But then there's a hyperparameter, which is how much rotation do you allow in the input data to your model? And you might translate that cat. That introduces at least one more hyperparameter. Typically in real world situations, we do some feature selection or some pre-processing of our data. And that introduces lots of hyperparameters, and not just the features that we use, but the way that we compute those features that we select. And then especially in use cases like autonomous vehicles, even the very data set that we decide to use can be thought of as a hyperparameter. And actually the data set that we decide to use can have the biggest effect on the model. You might say, why don't we use all of our data? And actually that's becoming more and more infeasible sometimes. And so often the first step in model training is picking the data set that we want to use. And I really think that we should think of that as a hyperparameter because it has outsized impact on the performance of the model. Okay, so why tune hyperparameters? I mean, the obvious reason is to get the maximum performance of your model. But there's another important reason, maybe it's the more common reason that people actually do tune the hyperparameters, which is that it gives you a way to understand the data that you're training on and the model that you create. So when you find out that a parameter has a big effect on your data, you learn something about your model and you learn something about your data. And in fact, I think that recently hyperparameter tuning has become more and more important for two reasons. One is that, deep learning creates lots more possible hyperparameters that we could affect, right? So the space of models that we might try, architectures that we might try, and data augmentation that we might try is getting bigger and bigger and bigger. So there's more things to try and more space to make great models, or more likely kind of shoot ourselves in the foot and not make a good model for a data. And deep learning tends to be especially sensitive to hyperparameters versus older machine learning techniques. And then also, I think we continuously get access to more and more computational resources, and CPUs get cheaper and GPUs get cheaper. And the thought is that computers are a cheaper resource than the machine learning researchers. And so the more we can let the computer guide our choice of hyperparameters, the easier it will be to get high quality models. So recently, I would say there's been actually an explosion of interest in automated hyperparameter tuning. So where do you want to start? I want to give you some kind of basic guidelines, and I want to make sure that you hear this. So make sure that your model works before you tune your hyperparameters. And I see people screw this up quite often, right? You kind of jump past the step where your model isn't working. And actually, when you find out there is a bug in your model training code, it's going to invalidate all your hyperparameter tuning. And I think Andrej Karpathy has the best resource by far on this. And he recommends choosing the simplest possible model and the simplest set of data. In fact, trying to overfit on a single batch as the first test that your model is effective, and then sort of progressing slowly through making your model more and more complicated, at each step being sure that your model is performing the way you expect it. And then I think there's another step, which is that you want to explore the data before you try to what's called exploit or find the very best possible set of hyperparameters. And so you typically want to try hyperparameters by hand, try a wide set of possible values, build an intuition for what they do, and then use sort of a coarse defined method where you start off with kind of a wide swath of values and slowly refine to more and more specific values. And then finally, at every step, it's important to ask yourself, am I overfitting or underfitting? Because you'd want to do opposite things. So by overfitting, I mean that your performance on the training data is higher than your performance on the test data. And if that's the case, then everything you do to make your model more complicated is going to make it worse. So if you're overfitting, you want to make your model simpler, you want to find more training data, or you want to add regularization like dropout. Now, if you're underfitting, and by that I mean that your model is performing about the same on your training data and your test data or validation data, then you have the chance to make your model more complicated and more powerful. So you might want to explore more things like model architecture. I think that it's quite important to build an intuition about the space that you're in before you start hyperparameter tuning, or maybe as you do hyperparameter tuning, because there's always more things to try than you have time or even compute to try. And because these parameters can interact with each other in complicated ways, there's an exponential explosion in the possible things to try based on the number of hyperparameters that you actually might possibly change. So I strongly recommend talking to a model expert who can tell you basic things about what hyperparameters are likely to change the performance of your model more or less. So for example, learning rate tends to affect models quite a bit, whereas the specific optimizer that you use tends to affect models quite a lot less. Maybe even more important than talking to a model expert is talking to a domain expert who can tell you things like what data augmentation techniques are likely to work and what data augmentation techniques are probably less interesting to try. In general, I'll tell you that things that you do to change the data or change the data pre-processing usually have an outsized effect on the model performance. So the data augmentation strategies and hyperparameters tend to be more important than the model hyperparameters, but they generally get less attention by academics. So if you're really trying to make models work in the real world, you're kind of on your own figuring out the data augmentation that you really want to do. Now, the main point of this talk is automatic hyperparameter tuning. So kind of once you have a basic intuition about the hyperparameters, how do you go about automating this process and finding a good set of hyperparameters and a high-performing model? There's sort of three traditional techniques and then some more complicated things that I'll touch on. So the kind of basic three strategies that people use is grid, which is kind of the simplest, random, which is also incredibly simple, and then Bayesian, which is much more complicated and one of those things that everyone thinks they should do, but often don't do because it seems too complicated to set up. Although I think Raytune makes it easy enough that really everyone should be doing it. So grid search is something that you might guess is a strategy you might come up with on your own, which is you basically take a discrete set of things to try for each hyperparameter that you have, and then try every combination of those parameters. So it's very, very simple to implement. It works really well. It's very systematic, so it's easy to kind of do analysis to find intuitions about what hyperparameters are effective and not effective. But it can get very expensive, right? Because you have basically you multiply together every number of discrete values you want to try for every hyperparameter, and that number can get really big really fast. Random search is maybe even simpler than grid search, and it's easy to implement. It's actually easier to do in a distributed fashion. And it typically works a little bit better than grid search at finding the best possible set of hyperparameters. But I think people use it a little bit less than grid search because it can be hard to interpret the results, and it can be hard to decide what distributions you want to pick for each hyperparameter. There's always an intuition here, which I think you'd kind of come up with on your own. It makes a lot of sense, which is to kind of do a coarse defined strategy, which means you kind of start off with a broad set of values over each hyperparameter, and then kind of zoom in on ranges of values that seem to be working well. But really, I'm here to talk about more sophisticated methods, which is, I think, where people should generally go. And the sort of general name for kind of being smart about hyperparameter tuning, or the most common strategy, is called Bayesian hyperparameter tuning. And so this is definitely more efficient than grid search or random search because it's a more principled approach, but it can be tough to implement from scratch. I really think that maybe over half of our customers that I've worked with at Weights and Biases kind of think they should be doing this, but never really get around to doing this because they feel like they're going to have to implement it themselves. And a few years ago, there really wasn't a good set of tools to do this, but I think RayTune, again, makes it so easy to do that you definitely should be doing this if you're not already. Finally, there's approaches, a general family of approaches that's really getting a lot of popularity recently called population-based training, where you actually train a whole bunch of things in parallel and then kind of kill off the less promising runs and replace them with mutations of the more promising runs. And this is really important when you have tons and tons of compute resources, lots of hyperparameters to try, and really big models. But this doesn't work at sort of small scale. So this is kind of the last thing that you want to do once you've kind of built up a real intuition around your model and you want to build the next GPT-3 or something like that. So let's go a little deep on how Bayesian hyperparameter tuning works. And I think this is a pretty simple algorithm that you might come up with on your own, but I'm surprised by how many people don't really know exactly how this works. So I think it's good to take a second to reflect on, if you had this situation, what would you do, right? So here I have an x-axis, which is my hyperparameter, and I have a y-axis, which is my performance. And these blue dots are actually models that I trained. So here I have some hyperparameter, and I trained it 4 times, and I got different scores each time, right? So I trained it with 2, and I got a score of 2. I trained the model with a hyperparameter of 3, and I got a score of around 0. And as is tradition in machine learning, I'm looking for lower values on this performance. So it's like a loss function where lower is better. So what would be the next point that you would try? And you might notice that this is exactly the same problem in some ways as a machine learning problem. We have an input number or a vector of numbers and an output score. And so you could imagine that we might want to create what's called a surrogate function. And we can use any machine learning technique for this. In this case, I use linear regression to create a surrogate function. And this basically models as a target the performance number, and as an input the hyperparameters that I have. So here I use a linear function, and I want to pick maybe the lowest value of the surrogate function. So here I would pick the value 0. And this sort of shows you why the surrogate function, just a linear regression, might not work well as a surrogate function. And even a more fancy model here, like this polynomial that I fit, still might not actually capture exactly what we want to do. Like, I think if you looked at these 4 points, you'd probably think, well, maybe I want to try something around 4, or maybe I want to try something way out around 10. Maybe I want to try 0. But this kind of fancier model is definitely suggesting that the best thing to try is 0, because that's the lowest value of the surrogate function. And that's why people typically use a Gaussian process or some approximation of a Gaussian process to fit this model, which you wouldn't normally use in a machine learning context, but you do use in a Bayesian optimization context. And the reason is that the uncertainty is incredibly important for picking the next set of hyperparameters that you want to try. So here we have a Gaussian process that's not just modeling the prediction, it's modeling the confidence. And I measured the confidence interval here in the shaded in area. So typically people don't pick the lowest value of the prediction of the surrogate function. They pick the value of that the surrogate function tells us is going to give the highest probability of something better than any performance we've seen so far. So there, that would probably be a hyperparameter of maybe 4.2 or 4.3, because you can see the confidence interval is wide and the predicted value is low. Another way of doing this, which is similar, is to pick the value where you have the highest expected gain over your best performing model that you've seen so far. And now this can be a little tricky to do in a distributed context, but Ray actually handles this for you very well. Another thing to try that's generally best practice, but lots of people don't do, is early stopping. So the standard way to do early stopping is a strategy called Hyperband. And there's a great paper that came out about this recently. And this comes from the intuition that over time, models that perform poorly in the beginning tend to perform poorly after lots of training data. So the strategy is to run the training for a set number of iterations, often epochs or sets of training data. And then you basically take the top fraction of models. Usually it's 1/3 of the top quarter of the models, and you let them run for another set of steps. And then you once again take the top third or quarter of the models and you let those run for a few more steps. And then finally, you're left with maybe just 1 or 2 models that you let run to the end. And while the Bayesian optimization tends to give you maybe a 2x factor improvement, the Hyperband can give you more like a 10x factor of improvement. So Hyperband, the effects are not subtle. It's very efficient and people should do it. But it can add complexity because it's hard to run in asynchronous context. And it's also not good for exploration because your models ran for different amounts of time or different numbers of iterations. So it's hard to gain an intuition from the results of a Hyperband early stopping search, but it's the best way to find the best possible model. So now I want to take you through a very concrete specific example using the WB and Ray integration and show you how this works. And you can follow along at home with this bit.ly link. So this is bit.ly/ray-wandb-example where we have more detail and more strategies and all the code snippets that I'm putting here. So I wanted to use training a GAN as the example. So again, here's this GAN as a model. It's a generative adversarial network that's trying to actually create digits. So this is a popular, a kind of a fun example of training. And it also is a very fiddly algorithm. So these awesome GAN examples that you see, you might not realize that they come from quite a wide hyperparameter search to find hyperparameters actually show you good examples. And I'll show you, these are actually the results of digits from 4 different models. And you can see the bottom right here where it's just absolute garbage is typical if you've ever really tried to train a GAN from scratch without someone giving you the best set of hyperparameters off the bat. So random search is the simplest way to do it, and RayTune makes it easy. And then RayTune's integration with W&B makes it easy to get these beautiful graphs where you can see what's working and what's not working. So here, each graph, each line in this graph is actually a different set of hyperparameters training a GAN. And the y-axis here is the score. Here, actually higher is better. And you can see that some of the models do well, some of the models do worse. Even some of the models start off doing well and then get worse, which is a hazard of training GANs. But you can see at the end, there's a wide range of performance of these models. You can also, in weights and biases, or if you kind of click through my bit.ly link, you can go in and you can look at this big table of the input configuration hyperparameter values and then the output scores. You can also dig in to any particular training run and see more detail on the performance and even the CPU metrics, and then finally the digits that got generated. So one of the awesome things about RayTune is that it's very easy to go from the random search to Bayesian optimization. It's just slightly more code, and we've actually given you an example here of that code. And it's going to make things more efficient, and RayTune will actually handle the distributed case beautifully for you. So when you run Bayesian optimization on the same data, you'll see that actually the models just perform a little bit better because it's able to use the performance of earlier values that it tries to inform the hyperparameters that it uses down the road. So here we trained 10 models again, but you can see that it's actually finding better performing models because it's being smart as opposed to picking random sets of hyperparameters. You can see that the performance actually steadily increases over time. The best case performance and the average performance is also increasing over time. Now, the final trick is to use Bayesian optimization with Hyperband early stopping, and this gets you the best possible performance. Here you only see 2 lines that really go out to the end because actually most of the early runs were cut off. And in fact, the red line here is equal to the performance of the Bayesian optimization run in the previous slide that I showed you without the early stopping, but we've just used about 10 times less computational resources. So you get the same result, but with way less expense on CPU. Now, some of the things that weights and biases gives you is something called parameter importance. And this is always a really interesting thing to look at. And you can look at this on this GAN, and you can see that there's actually 3 configurations here, which is a low number, but 2 of them are kind of anti-correlated with performance. That's why you see the red here. And then 1 is correlated with performance. We also do this thing at Weights and Biases that I really like that was inspired by Jeremy Howard, which is that we build a random forest on the hyperparameters to predict the output value. And then we take the importance score from the random forest. So from that, we can give you a sense of how much each configuration parameter affects the output score, even if there's no correlation. So for example, in an XOR situation where a hyperparameter might have a lot of effect on the output, but there's no linear correlation, we can find that through our importance metric. So if you sort the configurations by importance metric, that'll tell you if you want to go from coarse to fine or zoom in on a handful of configuration parameters and really optimize in your next hyperparameter sweep. That'll give you an intuition for which configuration parameters are most likely to be interesting to try. And this gets really interesting in larger searches. So, we have customers that will sweep over thousands of configuration parameters. And that's where Bayesian search, and especially distributed Bayesian search and early stopping, really gets important. And the configuration parameters get really complicated. And the importance metric becomes super important for figuring out how to find the best possible value. And then I'm a huge believer in exploring, not just kind of picking the top value of your hyperparameter search. And so we create these visualizations. Like an example is this parallel coordinates plot, where each vertical axis here is a dimension, and you can pick a range. So here I've picked a range of the highest accuracy values in a huge hyperparameter sweep that I did. And it shows me right off the bat, by just kind of following the yellow lines, that high accuracy is correlated with low dropout, and also high fully connected size and high L2 size, maybe not so much correlated with L1 size. And so you can actually click through that bit.ly link, and you can play with the parallel coordinates chart, and you can see for yourself how useful this simple exploration can be. Now, I want to leave you with a couple tidbits of general advice to make this go well for you. This is from talking to lots and lots of our customers who do different types of hyperparameter optimization in very different domains. This is kind of the best practices that I'll tell you. And I think, a very important thing is to start with kind of short runs and short sweeps. Like kicking off a gigantic hyperparameter search over lots and lots of parameters kind of seems useful, but often that data ends up getting thrown out when you realize that your whole approach was wrong, or there's a hyperparameter that you didn't consider that you then want to take into account for. So I would really say don't explore too much at once. Explore ranges of the data, kind of consider what's important, and then explore another set of hyperparameters or another piece of your data. It's very important to address underfitting, and Josh Tobin has a really excellent kind of set of things to try first or try later at his troubleshooting deep neural networks slides, which I strongly recommend. And he says, here's how to address underfitting, here's how to address overfitting. And you notice these are actually very different strategies. That's why I mentioned at the beginning, deciding if you're underfitting or overfitting is kind of an incredibly important decision point to decide what to do next. And then finally, I'll say, don't blindly optimize a single metric. So the downside of hyperparameter search is that you're really only picking one thing that you're optimizing, or maybe it's a combination of multiple things, but it can get you into trouble. And I'd point you to this bit.ly/WNB deep dive report that our deep learning engineer, Stacy, built for us. And she actually found different models on a semantic segmentation driving data set that had the best accuracy on cars and the best accuracy on humans. And you can imagine if you're building a self-driving car, the best overall accuracy is maybe not what you want if it has low performance on finding humans, right? I think predicting if there's a human in front of you is maybe the most important thing. Car is probably less important than that. Tree is probably less important than that. Maybe roads even less important than that. And I think a lot of the trouble that we get into in deep learning comes from optimizing a single metric. So hyperparameter search is a great thing to do, but it can get you into trouble if you blindly optimize a single metric. Finally, I'll say there's more detail if you follow this bit.ly I put at Ray WB example. And if you follow me on Twitter, I will post these slides here so you can follow along. And thank you so much. I hope that your hyperparameter searches are very successful.